I am Avinash Sathaye, Emeritus Professor of Mathematics at University of Kentucky, and today is February 25th, 2022. It is well established that the invention of the decimal number system was made in India, and later it was adopted by Arab scholars and eventually adopted by Western mathematicians. I, however, note that in Indian mathematics, the integers are indeed displayed in the decimal system, but fractions are often displayed as ratios of integers such that the denominators are suitably chosen integers which are kept as small as possible. This is in contrast with the usual idea of using powers of 10 as the denominator. This practice helps in keeping the calculation simpler and more accurate, and we don't have to fight with the numerical errors in computations with the usual decimal system. As a consequence, Indian mathematics is often based on number theory rather than the usual calculation of real numbers. We discuss two famous theorems in Indian mathematics to illustrate this. And whoops, okay. Sorry, this is the bottom of the screen goes out from me. Shall I stop and do it again? I mean, go to the next page. Let us start with this page now. The first part of the two theorems that I am talking about is called Kuttaka. We discuss the solution of an equation of the form ax minus by equal to c, where a, b, c are integers, and we seek possible integer values of x comma y. We also want to determine all possible such solutions, even though the solution set is infinite. The first manuscript describing the solution technique appears in the famous work Aryabhatiya of Aryabhata in 499 CE. Thereafter, it is a standard feature of almost all algebra books in ancient Indian mathematics. Indeed, Brahmagupta in his major work Brahmasputa Siddhanta in 7th century praises the topic in these words. Prayena yatah prashna kuttakara drutena shakyante jnatum vakshyami tatah kuttakaram sah prashnaihi. This means, since usually the questions in astronomy cannot be resolved without the Kuttaka process, I will describe the Kuttaka together with related questions. Brahmagupta devotes most of the chapter 18 to questions based on Kuttaka. In many questions, he adds an inspiration to the student by stating that a truly knowledgeable mathematician is the one who can solve this problem within an year. The Indian astronomy postulates first kalpa, which is a long period of time, and determines the number of revolutions performed by planets around the Earth in a kalpa. Here, the revolutions are counted on an average. The fictitious planet, which uses exactly the corresponding number of revolutions, is called the corresponding mean planet. We will discuss the use of suitable fractions for preserving accuracy and ease of calculations below. So, now this page and the next page are going to have some complicated mathematics, so please bear with me. As stated above, we are trying to find a complete solution to ax minus by equal to c, where a, b, c are integers, and we are looking for integer solutions. We begin by breaking the equation into a new equation, where a and b are smaller. Specifically, we divide a by b and find the remainder r. So we write a equal to b cube plus r. This breaking is called Kuttaka. from the word kut. Root kut means pounding or pulverizing. Now, I have done this substitution and shown various simplification stages. It's only the last one that we need to pay attention to. The new equation becomes Rx1 minus By1 equal to C, where we have renamed x1 as x and y1 as y minus qx. So notice that the two coefficients R and B are smaller than the original coefficients A and B. Thus, the new equation has smaller coefficients, and the original solutions can be recovered from the new ones by this substitution. Thus, we reduce the original problem to smaller coefficients and until the last equation is easily solvable. So now we set up an example of a sizable equation needed in astronomy. This problem comes from Bhaskara 1, his book on Laghu Bhaskariya, around 600 CE. The equation that you finally get to solve is this huge equation, this 36641 divided by something times x minus y equal to this number 24 over that same denominator. Now, if you ask a modern student to solve this equation, he will promptly convert it to a decimal number using a 10-digit precision. And as you can see very well, that this equation is rather difficult to solve. We'll have lots of numerical problems. And in particular, this number for most calculations would be treated as a zero. I mean, so it will destroy the original sense of the equation. So we can, as one can easily see, that any further work is unwieldy and likely to cause numerical errors. A Kuttaka student, however, will multiply by this denominator and write down this new equation. So 36641x minus this big number times y equal to 24. Now, even though these numbers are huge, there is no additional numerical problem now because it's over integers. Then I'm just writing down the answers. I'm not going to go through the steps, of course, but the answers seem to be x equal to this number 346688814 plus this other number times t. And what is t? I will explain it in a minute. And y is 32202 plus some t. So let's give the meanings of what these numbers are. So the 24 in the original equation is called the residue of number of revolutions of Saturn. This means Saturn has completed 24 divided by this number, that much revolution, in the current cycle. X denotes the number of days elapsed from the beginning of the current epoch. And Y denotes the number of completed revolutions. So once the revolutions are complete, so it's saying it's gone through some 32,000 revolutions. And at the end, this is the revolution that it has gone through. The parameter t is simply a non-negative integer. It can be arbitrarily chosen, but the value t equal to 0 gives the minimum values of x and y. So now I want to switch over to the second theorem. The Chakravala is the simple generalization of the linear equation for Kuttaka. Consider an equation of the form ax squared minus by squared equal to c. The old one was ax minus by equal to c. After some manipulation, this reduces to the problem raised by Brahmagupta himself in the same chapter on Kuttaka, namely So he doesn't use A, B, he uses a C, of course. So assume that n is a positive integer, which is not a square. Determine all solutions of the equation x squared minus ny squared equal to 1. This is called the Chakrawala equation, where again we seek to determine all integer values for x and y. This problem turned out to be a much harder problem, and it was completely solved by Bhaskaracharya in his book on algebra entitled Bijaganita in the 12th century. During the intervening 500 years since Brahmagupta, various mathematicians in India attempted to make progress on this problem. One important name in that list of mathematicians is called Jayadeva. Very little is known about him. He was in the 10th century, and his all works are lost except for a brief description of his attempt in a commentary on a different work. His ideas were evidently close to the final solution by Bhaskaracharya, but he was unable to finish the needed inductive steps. In fact, Bhaskaracharya gives credit to several earlier mathematicians and only claims a credit for himself for finishing their work. Unfortunately, Jayadev is not on that list. In the Western world, the problem itself was unknown until 1656 CE, when Fermat formulated the same problem as a challenge to fellow mathematicians. Specifically, he asked for solutions to the equation x squared minus 61y squared equal to 1. It's interesting to note that Bhaskaracharya had shown the solution to the same problem, same equation, and many others in his treatise. He also used the Brahmagupta's theorem described below. So, Fermat's challenge led to the intervention of the theory of continued fractions by Brunker and Wallis. Finally, a complete solution was found by Lagrange in his appendix to Euler's book. In the Western world, the equation is named as Pell's equation, who only introduced its proof in his book, but Euler credited it to him and it has stuck. Continued fractions have been very useful in different parts of mathematics, even though they are not taught in a regular mathematics curriculum. It was shown much later by Selenius in 1975 that the steps adopted by Bhaskaracharya give a shorter sequence of the usual continued fractions, and his paper also reports on Jayadeva's work as far as it is available through the commentary. I have recently made some changes, some modifications to make the Bhaskaracharya process more efficient. The Chakrawala process only needs use of pairs xy which are just x comma 1, simply means y. You can always take y equal to 1 for developing the answer, together with a process called bhavana, which is a multiplication process. And this simplifies the work and produces the compact answers. So we write our answer as a sequence, and then if you want the final integer value, you can calculate it. Now, I found out that determining all C for which n comma C problem has a solution is equivalent to n comma 1 solution, that means our Chakrawala solution, with the current results in number theory. However, I mean, the number theory solutions are rather complicated. I, with my student Stuart Wong, oops, just jumped. Okay, I, with my student Jason Wong, have found a way of found a way of answering this question by using Bhaskaracharya's own process. And we use Iyengar's proof of the Chakravala result in the process itself. And oh, sorry, I cannot go down enough. Okay. Well, let me just say from memory. So we use Iyengar's proof for the Chakravala process, and from that we gave a complete solution to the NC problem, which C's have a solution. Brahmagupta, so now I am coming back to Brahmagupta's theory. He considered a more general question, namely the NC problem. And this problem asks us to solve the equation x squared minus ny squared equal to C, and that's the generalized Chakravala equation. Here C is some non-zero integer, and we seek to find integer solutions. In this context, he established the famous formula called Bhavana. It says that given two solutions of the generalized Chakravala equation, so one solution is called S1, which has components x1, y1, c1. S2 is similarly x2, y2, c2. Their product, denoted by S equal to S1 star S2, is also a solution of the same equation, where S is given as x, y, c, and the formula for x is simply the product of the x's plus n times product of the y's, and y is the cross products of x1, y2 plus x2, y1, and c is just the product of c1, c2, the two numbers here. And so note that we have intentionally left our n out of this definition to shorten the display. The first step is it is clear that what's going on here? Okay. So the first step of solution is the case where C1 and C2 are both -1. Then the product x, y, 1, then the product becomes x, y, 1 and the Chakravala, what I don't see here is it's the product of x, y, 1 with itself, and where C1 and C2 are -1, both -1. And then the product gives me the xy1, that's the S, has 1 as its last number, and that means the Chakravala problem is solved. It's immediately obvious that we don't hope to find such C1, C2 for our chosen n. It is also easy to see that the product is only likely to increase the absolute value of C, and thus we will never reach the desired 1 by just multiplying. However, if x1 and x1 y2 plus x2 y1, that's the y value, is divisible by C1, then the last two entries, y and C1, C2, are both divisible by C1. It is easy to show that then x is also divisible by C1, and Brahmagupta notes that since x, y are both divisible by C1, we get a new triple, x over C1, y over C1, c over C1 squared. Thus, using the new triple, we get a reduction in the value of C. It's no longer just C, the product, but it's divided by C1 squared. This process of bhavana, followed by the reduction process, I propose to call it vibhavana. That's a variation of the bhavana. As an illustration, we prove one of the first theorems of Brahmagupta. It says that if we have S1 as x1, y1, 2, and then we take the Vibhavana of S1 star S1, then it is a solution of Chakravala. To see this, you just write S1 equal to S1, and that each one is x1, y1, 2, and then S1 star S2. I am just asserting that it becomes x, 2x1, y1, and 2 times 2. And we do the division for the first x and, we do the division, and then as asserted above, x is then automatically divisible by 2, and the solution is x over 2, x1, y1, comma 1. So that's the success. So what Brahmagupta did is found the first few solutions, and later on it turned out that for the final answer, it's enough to take multiples of x1 or x1, 1 something, and you don't need the different value for y. Then when you multiply, the product of the c's gets bigger, but we use the y1 so that it gets divisible by the first c1, the final answer. And so you go up and again come down. Unfortunately, that's not it. Unfortunately, when people attempted it earlier, they found out that these new numbers that you keep on getting are not necessarily just going up or going down. And that's where Bhaskaracharya came in, and he showed that eventually, if you choose your numbers carefully, in other words, choose as minimum as possible, then it will reach that 1.